Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is Lecture 3. We are in Part 3 of Chapter 2, Simple Comparative Experiments, and we are in the subsection of ANOVA and Design of Experiments. Last time we talked about a model for the two-sample test. And so we have observations, Yij, and these were defined in the last video lecture. So Yij is the jth observation under the ith treatment. And here we have two treatments, 1 and 2. Mu sub I is the mean of all the observations, the mean of the ith treatment level. So continuous, we're usually in the continuous situation, so not of observations, but of the distribution or population. And then epsilon ij is the random error associated with the jth observation in the ith treatment level. So these two go together directly. And then this is epsilon ij these are assumptions. The assumption is that the random errors are normally independently distributed with mean 0 and variance sigma sub I squared. So within each treatment level, the variance within the treatment level of all the observations in that treatment level are identical, but not necessarily identical to other treatment levels. So there could be a different variance depending on the different treatment level, and that is what this model allows. Now this implies that Yij is normally independently distributed with mean mu sub I and variance sigma sub I squared, and we went over how that was derived or reached at last video. Okay. The next topic we discussed were the types of error, and so alpha equals a type 1 error, and this is the probability that we reject H naught given H naught is true. So that's an error. We should not do that, right? And so that's what alpha is. Beta is a type 2 error, and that's the probability of not rejecting or failing to reject H naught when we should, when H naught is false, given that H naught is false. All right. The structure for a hypothesis test has 5 steps. The hypothesis statement, and in this course, that's going to include also a statement of the model and the significance level, alpha. The second step is a test statistic. We went over both of these last time. And in this video, we're going to go over the last 3 steps, the critical region or rejection criteria, how to make the decision, and the concluding statement, the conclusion, a way to communicate this not only to other statisticians, but to lay people as well. So as we said, the hypothesis test for the two-sample test is we could have distributions that look like this. So the first distribution could have a mean over here, the second a mean over here, and our hypothesis statement is that the two are the same. So in other words, these would be on top of each other, so to speak. Now, since we have the possibility of 2 different variances, or standard deviations, the way it's written there, we might, even if they have the same means, we might have something, one of the distributions might look like that compared to the other. Okay? So they could have the same mean, but not necessarily the same variance. Now, the hypothesis statement is always written with an equal sign. And if I want these 2 hypothesis statements to be the same, then this would be 0, because if I subtract mu2 from both sides in the top line, I get mu1 minus mu2 equals 0. And then the same thing over here. If I want these to be equivalent statements, then I need to rewrite it here. Now, what I'm saying by having a mu naught here is that you don't have to test that they're equal. You could test that there's a difference between them of a certain magnitude. Okay, and that's a very specialized case, though. So in practice. So be careful with H naught. Remember that because we have an equal sign here, the probability that the null hypothesis is actually true is 0. We're using the null as a baseline, so H naught is used to calculate probabilities. So in order to determine whether or not the claim is true, we need to know the probability of it occurring, of our sample, the characteristic we're calculating from our sample occurring under the null hypothesis. And if it's very, very small probability that this would occur if H naught is true, then we would reject H naught in favor of the claim or alternative hypothesis. Okay? In most cases, the alternative hypothesis is what we're trying to prove, but not all. Okay. We went over the parameter estimates and how the sample or the test statistic was calculated in the last video. We also discussed how the variance was calculated for the test statistic. And so we said we could use this statistic if both the variances are actually known. So when that happens, then Z naught under the null, under H naught, Z naught is a normal 0, 1 or a standard normal distribution. But that's only under the null. Okay? We talked about 4 different ways, 4 different test statistics. So if the variances are known, then Z naught under the null, under H naught, Z naught as a standard normal distribution. Okay, so if we have a large enough sample size but we don't know the variance, then we can say that using the CLT, again, under the null, Z naught has approximately a standard normal distribution. We're using the CLT to make an approximation. And then if the variances are unknown but equal, and I want to point out and stress that we have to test this. And at the end of this chapter, we will, or later in this chapter, I should say, we will show how to do a formal test. We have to test this. You can't just say, oh, well, they're close enough, I'm just going to assume they're equal. No. Do a formal test, or else you may be making a bad assumption. Okay. We like the case where they're equal because we have the degrees of freedom, 1, are easier to calculate, and 2, this is not as a conservative as a test as if we don't know the variances. We have a small sample size, and they're not equal. If they're not equal, you'll notice that the calculation here and here are the same, but the degrees of freedom is calculated using this lovely little formula. So under the null, T naught here, where the variances are equal, has a T distribution with N1 plus N2 minus 2 degrees of freedom. When the variances are not equal and small sample sizes, we have the Welch's t-test. In this case, I'll write it up here, T naught has a T distribution with nu degrees of freedom, where again, we calculate nu with that lovely formula. All right. Let's talk about the critical region. So the critical region is the term that is most used by statisticians. Probably the term that I like the best is called the rejection criteria. I like to call it that because we have in this table, we have the criteria under which we will reject the null depending on which alternative statement we have or alternative hypothesis we have. All right. So the alternative hypothesis determines the rejection criteria for the test. The null hypothesis is always the same, mu1 equals mu2 in this case, for a two-sample test. So if I have a less than, mu1 is less than mu2, then I expect z naught to be negative, because remember, z naught, the numerator is y1 bar minus y2 bar over a positive number. So if mu1 is less than mu2, I expect y1 bar to be less than y2 bar. And so z should be negative, and therefore I'm going to reject when z naught is less than negative z sub alpha. So let's take a look at this. So again, the null hypothesis, mu1 equals mu2, I'm going to go down here. So I guess I'll start with this case where mu1 is greater than mu2. The reason I'm starting with this is because of the definition of a critical value, z sub alpha. Remember that z sub alpha, that is a critical value, and it's a positive value as long as alpha is less than 0.5, and that is the usual case. So we like small alpha. So if we're using a small alpha, which is reasonable, then z sub alpha would be positive. And z sub alpha is the value such that the probability that z is greater than z sub alpha is, that probability is equal to alpha. And so the probability or area to the right of z sub alpha is alpha. Okay? So what this says is under the null hypothesis, we expect z naught to be very close to 0. Okay? Because the means are equal, so we expect the sample means to be close to the same as well. When z naught is far away from the mean, under the alternative hypothesis, it would be very positive. And when the probability that we have a z naught as small, so when that probability is very small that we get this z naught under the null hypothesis, we want to reject the null hypothesis. So when the difference between the sample means is way too big, then we want to reject. And in this case, we're saying that y1 bar would be much larger than y2 bar, so we'd have a positive z naught. And so the rejection region, since the total probability of rejecting the null when the null hypothesis is true is alpha, then in order for us to reject the null, z naught has to be more extreme than z sub alpha in this case. Okay? Because the probability that we're as extreme or more extreme is alpha. The probability we're going to reject the null when the null is actually true is a max of alpha. Okay. So this is an alternative of greater than. An alternative of less than means that y1 bar minus y2 bar should be less than 0, because y1 bar would be less than y2 bar. And it would be very far away from 0. Under the null, we would expect that difference to be close to 0. So if it's not close to 0, under this alternative hypothesis, we expect z naught to be very negative, because y1 would be a lot smaller than y2. And so, again, the probability that we're going to reject the null when it's actually true is alpha. So here we would need the negative of the critical value. So we'd have negative z sub alpha. And if z naught is as extreme or more extreme than z sub alpha, if it's in this region here of less than negative z sub alpha, then we're going to reject. So this is the rejection region. Okay, so this, when z naught is less than negative z sub alpha, we're going to reject. Just like up here, if z naught is greater than z sub alpha, we're going to reject the null when we have this claim. Now, the claim that gives students the most trouble is the last claim, where we're testing not equal to. And in this course, we're going to be testing not equal to a lot. So it is important for us to understand this case. So here we're saying that all we care about is that mu1 is not equal to mu2. So whether z naught is very negative or whether it's very positive, doesn't matter to us. We want the probability of rejecting the null when the null is actually true to be a total of alpha. So what we do is we split it up into the two tails. So half of it here and half of it here. And when we add these two together, we get alpha. So now we have to adjust our critical value. So instead of alpha, we have z sub alpha over 2, because that's what, the subscript here is this. This is the probability that z is greater than z sub alpha over 2, the subscript, right? So if alpha over 2 is up here and alpha over 2 is up here, then we have two zones where we could reject the null. If z naught is less than negative z sub alpha over 2, then we will reject the null. If z naught is greater than z sub alpha over 2, we will reject the null. Now notice z naught is going to be one number. It can't be both negative and both positive. Zero's here. So either you're going to have this case or you're going to have this case. You can't have both at the same time. So if z naught is negative, then we look at this criteria. Z naught less than negative z sub alpha over 2. If z naught is positive, then we have to look at this case here. Is z naught greater than z sub alpha over 2? Okay? And these are so if z falls anywhere over here, we're going to reject the null. And if z falls anywhere over here, we're going to reject the null. Either case. All right. So I've given the cases for, two cases are combined here. In the first column, we have the variances are known. That would be this first test statistic. Variance is known. Or we have a large N, and we use the same test statistic, except that now instead of sigma, we have S's here. So we'd use this test statistic, see a large sample size. And so it's the same way that we calculate, except now instead of sigma, we have S. And in both cases, we say that Z naught, we're assuming it's close to a standard normal distribution. When we have unknown variances and they've passed the test that says they're equal, then we can use this set of criteria depending on our alternative. When they do not pass the test for equal variances, then we have to use this set of criteria, again where nu is calculated using the Satterthwaite degrees of freedom calculation. Okay. Now let's talk about the other method of specifying a critical region. It's always the same. It's that the p-value is less than alpha. So the p-value is the probability of obtaining a value of the test statistic, z naught or t naught, whichever one we're using, that is as extreme or more extreme. So that can be said as at least as extreme as the one that we observed, z naught or t naught, depending on what we're doing. Okay? Now, for an alternative of mu1 less than mu2, the p-value is going to be the probability that z is less than z naught. Let's take a look at this. Okay. So in this case, what we're doing for the p-value method is we're looking at z naught, and we're going to calculate if the claim is that mu1 is less than mu2, then we expect z naught to be negative, because we've said that y1 bar minus y2 bar, that should be negative, because y1 bar should be smaller than y2 bar. So we look at this, and we say, okay, if z was less than or equal to z naught, this is going to equal the p-value. And if the p-value is less than alpha, that means the same thing as we had before. Here's negative z sub alpha. Remember, alpha is the area to the left. And we said if z naught falls anywhere to the left of negative z sub alpha, we're going to reject. So let's say, so the area the total area to the left of negative z sub alpha is alpha. So if z naught is somewhere to the left, if it's less than negative z sub alpha, then the probability of being as extreme or more extreme is going to be here. This area has to be less than alpha. So that is how we get the rejection region for that case. Now, what about the alternative when mu1 is greater than mu2? Well, in that case, we expect y1 bar to be greater than y2 bar in practice, and so that would make our test statistic positive. Okay? So under the null, again, the test statistic should be close to 0. So under this claim, the test statistic should be very positive. Again, before we said that this area to the left of z sub alpha, or to the right of z sub alpha, above it, is alpha. And we said that the rejection region was when z was more extreme than z sub alpha, when it was further away from 0 than z sub alpha. So it would be greater than z sub alpha. So if that's the case, let's say that z naught is right here, then again, the area above this would be this area, and it's clear that this area is less than alpha. So again, p-value less than alpha means we reject the null. Now, this is the p-value here, and this is the p-value for this case. So again, the more confusing case is the not equals to, which again is the case that we're going to use the most. So I don't know what exactly happened to my drawing for that, but we'll draw another one. All right. So in this case, we have two cases. We have if z naught is less than 0. Okay. So H1 is that mu1 is not equal to mu2. We don't care if mu1's bigger than mu2 or mu2's bigger than mu1. We just care that they're not equal. So under the null, again, the value of the test statistic is going to be close to 0. Under the alternative, it's going to be farther away. And so remember before we had negative z sub alpha over 2, and this area was alpha over 2. And we had positive z sub alpha over 2, and the area over on this side was alpha over 2 for a total area of alpha. So the total probability that we will reject the null when the null is true is alpha. And we said our rejection region was z naught over here or z naught over here. Now, if z naught is less than 0, then let's say that we have a z naught here. So z naught is there. Well, we're interested in z naught being as extreme or more extreme, z being as extreme or more extreme than z naught. But it could be over here too. This would now be the negative of z naught in this case, which would be a positive number because it's negative if it's over here. We want both of these areas, and they're the same amount of area. So this is the probability that z is less than z naught, and this is the probability that z is greater than negative z naught in this case, which is a positive. We want to add those two together, and they're the same area, so 2 times this is the p-value. You could say that it's the probability that the absolute value of z is greater than negative z naught in this case, because we've said that z naught is negative. Okay? And, all right. So, and that would equal 2 times the probability that z is less than z naught, since z naught is negative. Now, in the case where z naught is positive, so in the case where z naught is positive, Okay. Then we want to know, then what we need, the p-value, is going to equal the probability that the absolute value of z, the distance from 0 to z, is greater than z naught, if z naught is positive. Okay? And this is going to be 2 times the probability that z is greater than z naught. Okay? And again, if we had z sub alpha over 2 here, then that would mean that all of this shaded area would be alpha over 2. Okay. And negative z sub alpha over 2, all of this shaded area would be alpha over 2. And so if this is z naught, then the area above z naught would be less than alpha over 2, and 2 times that would be less than alpha. Okay. This is for z naught greater than 0. So this area would be the probability that z is greater than z naught. And the p-value, 2 times this, is equal to the p-value. So when we're doing a one-sided test, we can find the p-value directly. When, see here, oops, here, or here. But when we're doing a two-sided test, a not equals to for the claim, then we have to multiply the area that we find away from 0. We have to multiply that by 2, okay? So we have to multiply by 2 when we have the not equals to. All right, so I hope that explains the p-value. Most of you have had exposure to this already, but I want to explain it again. Okay, and then the decision is the 4th step. Now, if the rejection statement or criteria is true, so let's say that we have rejection region was z naught less than negative 1.96, and we calculated z naught was a negative 2.0. So then we'd say negative 2. So let me write this out with steps. So this would be negative z sub alpha, and let's say that z sub alpha equals 1.96. Then we'd have negative 2.0 is less than negative 1.96, and that would be true, so we would reject h naught. Now, what if we had z naught was equal to negative 1.00, and still negative z sub alpha equals negative 1.96? Then we'd have z naught less than negative z sub alpha. So we'd have negative 1.0 less than negative 1.96. That's not true, so fail to reject h naught. And that's what we're saying here. If the rejection statement is true, reject it. Reject h naught. If it's not true, we fail to reject h naught. Okay. So now, our decisions are, all of our probabilities are based on h naught. But when we get to the conclusion, we're now going to talk about the claim, which is h1. So now we're looking at this in reverse. We're looking at this in terms of the claim, and the claim is h1. So if reject h naught, then there does exist sufficient evidence to support the claim. So this would be does. If we fail to reject h naught, there does not. So if we do not reject h naught, there does not exist sufficient evidence to support the claim. So we either put does or does not. If we reject the null, then there does exist sufficient evidence to support the claim. That's what it took in order for us to reject the null. If we fail to reject the null, then there does not exist sufficient evidence to support the claim. So the baseline is that we're going to not reject the null unless there's overwhelming evidence that it's not true. Okay? So the hardest part of this statement is to put H1 in words. Okay? Okay. So we need to express, so you're going to have something like mu1 is not equal to mu2. And say this is the test, for a pain reliever, the time to pain relief of drug A, and this is the time to pain relief for drug B. Oops. And so we would say something here like the claim that the time to pain relief for drug A and drug B are different. Okay? And so we might say which pain relievers they were, Advil and Bayer or something. And then I want to point out that I stress that we should use the confidence level in this because we want everyone who might read this to have an intuitive idea of what we mean. And so here, this is 1 minus alpha in percentage. You could say 100 times 1 minus alpha percent. That's fine. Percentage is just the units. So 0.02 and 2% are exactly the same thing. They're just different units. Okay? So the reason that I say use the confidence level and not the significance level, which a lot of people do, is because if I say this to somebody on the street, I am 98% confident, at a 98% confidence level, they know right away that I'm 98% confident that what I've said is true. But if I say a 0.02 significance level, they're like, is it a 2% that it's true? Or, they're just thinking the 2%. They're confused. They don't know what it means. So we should take that confusion away from them and use a term. It's technical. They won't know what a confidence level really is, but they'll have an idea, that intuitive idea that will match up with what we're trying to tell them. Okay? So please use the confidence level in these concluding statements. And don't mess with the wording. Because if you mess with the wording, you may say something that is no longer true. And if you say something that is no longer true, technically speaking, then points will be deducted. Okay? So statistics has nuances, and we've written this statement in such a way that the nuances are taken care of, so you don't misstate it. Okay? All right. And then we need to make a statement about the sample size. And so I've put a very simple statement about the sample size. Later on, we may have to modify this to reflect what we're doing, where we have multiple treatments and multiple levels of the treatments, let's say, so 2 factors. Then we want to tell something about the sample size that is informative to the person who's looking at it. Why do I care about the sample size so much? Well, if you do a study and say you're 99.9% confident and you used n equals 5 for your test, that means that your power is probably very low. Okay? So you've controlled your type 1 error. Confidence level, significance level, they're tied together. So you've controlled that. You've set that. But if your sample size is small, then I know that your results are volatile, that you could get a very different result with a different sample because it's such a small sample size. So the calculation of your test statistic could vary quite a bit with a different sample. Okay? And so therefore, the power of your test is going to be low. And if you have a large sample size, then I know that the power of the test, the results, they're more consistent. you're going to have a higher power. Also, you'll learn that if you have a balanced sample size in your different treatment levels, your power is increased. And if you're unequal, your power is decreased. So this sample size tells us a lot. They're important. So please use this. If you want full credit, you want to use this statement and in every hypothesis test that we perform in this class. All right. Well, that's enough time for this video. So in the next video, we will go over an example of all of these steps. Please, if you haven't already, update your formula sheet for your homework and projects. Now, I would certainly put the formulas for the test statistics on my formula sheet, however you want to organize it, but be able to find it quickly. I also strongly suggest that you put your rejection criteria on there so that you can quickly and easily find that and understand it. I've given you a very nice table so that you can easily and quickly come to the correct decision. If you will plug in values, write down that formula for your rejection criteria, substitute in the values, and if the statement's true, reject. If the statement's not true, fail to reject. Depending on your decision, you can easily write your conclusion with the two sentences that I've given you. All right. I hope this has been helpful. If you have questions, by all means, come to virtual office hours. If you need an answer urgently before office hours, then by all means, email me, and I will get back to you as soon as I can, as soon as it's possible. Please take care of yourself because we hope to see you next time.